Greetings and welcome. My name is Brian Waddy, and today we're looking at some more complicated completing the square examples. So more on comp the square. So there's a couple types of examples that can be a little bit trickier that I conveniently avoided in my last video. Suppose I'm solving this by completing the square. X squared plus 5x minus 10 equals 0. So let's follow through the steps. So step 1, and the steps, by the way, are found at the end of the last video, so you go back and refer to that if you need to, but I will verbally recite them here. So step 1 is move the old c term to the other side. So that's my old c term is the 10. And I leave these blanks here in anticipation of adding something to both sides. Step 2 is find the new c term. And the new c term is found by the formula b divided by 2 all squared. So for us that's 5 halves squared. And this is where this problem reveals its difficulty. In the previous examples, we had an even coefficient for our linear term. However, now I've got an odd one, and it's unfortunate because my formula works out much nicer anytime it's even, because the even numbers are divisible by 2. This one, however, does not. And I understand you might be tempted to say, oh, that's 2.5 squared, blah, blah, blah. But no, actually, don't use decimals, all right? Don't use decimals. We're going to keep this as a fraction. And yes, 5 halves does not reduce, but that's okay. Because I can use my properties of exponents, in which I'm going to square both the top and the bottom here. And 5 squared is 25, and 2 squared is 4. So this is my new c term. And even though you might not like fractions, we're going to add my new c term to both sides. All right, so I'm going to add 25 fourths to both sides. So this left-hand side, even though it looks really crazy, we actually can factor that very quickly, in which I know that it's going to be the square of some binomial. All right, I call this fast factoring as the step in completing the square process. I'm going to have x with something all squared, and that something, recall I said, is what I had right before I squared it when finding my new c term. So this is going to be a positive 5 halves. By the way, the other place you could find it, if you didn't grab it there, is it's just going to be half of your b term. So 5 divided by 2, right? 5 halves. Okay? Or half of your b, rather, not b term. So that is not that bad to fast factor that. However, it's a little bit more work on the right-hand side simplifying here. I need to find a common denominator here, so I'm going to multiply by 4 over 4. And I've definitely got some scratch work. Feel free to kind of like write your scratch work on the side. So 10 times 4 is 40. I'll write this out. 40 fourths plus 25 fourths. That's going to add to be 65 fourths. All right, this is my work on the right-hand side. Which, by the way, sometimes people do this calculation somewhere else. So feel free to do that if you'd like. Wouldn't matter to me. But still write it on your paper so that way you can get partial credit in case somewhere you make a mistake. So let's see. Let's keep solving here. So now that I've got this square of a binomial, this was the convenient thing about solving by completing the square, is I can just root both sides, and plus or minus, don't forget it. Don't forget it. And let's see, on the left-hand side, this just cancels out quite nicely. Left-hand side always seems to be the easier side here. So I get x plus 5 halves. And the right-hand side, recall that a square root is the same as something raised to a fractional exponent. So I'm able to use the same property of exponents that allows me to distribute to a numerator and denominator, or distribute over division, I can use that same property with a square root. So this is actually going to be the same as plus or minus the square root of 65 over, and the square root of 4 I actually can calculate is 2. And I'm actually quite certain that every time we solve by completing the square, your denominator will end up being a perfect square that reduces nicely. So then I don't have to worry about rationalize, right? If this was like square root of 3, I'd end up having to multiply and rationalizing. It'd be a lot more work. But it does actually work out quite nice each time. And then the last step for completing the square is let's just solve. So subtract 5/2 from both sides. So I end up with 2 answers. In this case, I would not have been able to get them by factoring, but I get exact answers by completing the square. And if you wanted decimal approximations, oh, I forgot my minus sign there, plus or minus, that's where the second answer comes from. If the square root of 65 could have been reduced, I should have done that, but I don't believe there is a perfect square that goes into 65, right? So I'm all set. And if you wanted a decimal approximation, you could actually calculate this out and do so. And actually, there is another way I could write this, since these have common denominators. I could write that as -5 plus or minus the square root of 65 all over 2, if I'd liked that better, right? So it's a little bit trickier. Really, it was just algebra that made that problem more difficult, or arithmetic, where I just kind of had to be careful with my fractions and etc. Careful with my square rooting this fraction so that I did it correctly. But really, it followed exactly the same process. So that's the first type of quote-unquote tricky problem when solving by completing the square. Let's look at the second type. What if I'm solving this problem? Let's say I've got 3x squared minus, let's see. There's technically, I'm going to go for a moderately tricky problem. There is one of more difficulty, but we'll actually figure that out in class together maybe. So 3x squared minus, let's say, 6x plus, let's say, 10 equals 0. So what's interesting about this problem is that unlike all of our previous examples, we had a positive 1, a little hobbit wearing a ring, invisible in front of our squared term. And now I don't have that. But one of the convenient things about mathematics is if I can reduce a problem to a previously solved type of problem, then I know I can solve it. So if I wanted this to be a 1 here, what could I do to this problem to make that a 1? And the easiest thing is, oh, what if I could divide by 3? So I'm going to divide everybody by 3, and since I'm doing it to both sides, it is a legal math move. And let's simplify this. So I'll have x squared minus 2x plus 10 thirds equals 0. Right? And now I've reduced it back to a previous type of problem. And let's solve this because this does have some fractions and might be worth noting. So minus 10 thirds from both sides. This is the first step when solving by completing the square, which is move the old c term. X squared minus 2x blank equals negative 10 thirds blank. And let's calculate our new c term. And actually, I'm going to do that on the side this time. So our new c term is negative 2 divided by 2 all squared. So that's negative 1 squared, which is 1. So I'm going to add 1 to both sides. Right? And my left-hand side can now fast factor. I've created a perfect square. I've completed the square so that this factors into be x with something all squared. And what was that something? It was what I had right before I squared it. It's going to be that minus 1. And the other place it came from was half of my b, right? Half of negative 2 is negative 1. So those are the two spots you could find that value. equals, and let's see, I've got a little bit of fraction work, but not terrible. Let's see, so negative 10 thirds plus 1. I'd need a common denominator. Currently this is over 1. So I'd multiply by 3 over 3. And I'd have negative 10 thirds plus 3 thirds. Right, so that's going to be negative 7 thirds. And yeah, this is actually an uglier problem. And I think I broke my promise about these denominators always simplifying nicely already. That was quick. But most of our problems, they work out that well. So let's see. So the next step is root both sides. Plus or minus, don't forget it. Now, careful with this minus sign. It is supposed to be there, according to this problem, in order for me to do everything correctly. So I do have to take care of that. So let's see, on the left-hand side, these cancel out. I get x minus 1 equals plus or minus. Now I've got the square root of a negative. What is the square root of a negative? Well, that is I, and the square root of 7 is the square root of 7, all over the square root of 3. And I'm not allowed to have a radical in the denominator, so I'm going to multiply by square root of 3 over square root of 3 to deal with that quickly. And at the same time, I might as well add 1 to both sides to get x by itself. So I'm kind of combining two steps in one, simplifying and solving. So I'll get x equals 1 plus or minus I times root 7 times root 3 is square root of 21 over root 3 times root 3 is root 9, which is 3. Right? And those would be my answers. So here's an example of a problem that has no real solution because of this imaginary part. So this is absolutely not factorable for us, at least with integers. And it ends up having imaginary answers anyway. So if I was referring to a parabola and its x-intercepts as these solutions, this would be a parabola like this, where it never crosses the x-axis, something to that effect. It would be a kind of a graphical representation of what's going on. So yeah, so those are kind of two difficult or trickier problems when solving by completing the square. Sometimes if you have an odd number as your b term, you end up with fractions you have to deal with. And then the other situation is anytime your a is not 1, your first step you kind of have to divide through by that a value. So those are two tricks. There's kind of one trick that's kind of a modification of both of those, but I'll let you guys struggle with that a little bit on your own and see how that works out. Alright, thanks for watching my video. I look forward to seeing you guys next time. Bye-bye.